I'm an assistant professor at the University of Wisconsin-Madison, and my group also does modeling, primarily thermohydraulic modeling and tritium transport and system-level modeling. But I will not be talking about modeling in this talk at all. I'll only be talking about some of the experimental work that we do and some of the thermodynamic interpretation of the experiments that we do around 3 interesting case studies. And I would like to acknowledge that this work is funded by the U.S. Department of Energy Nuclear Energy Department and the U.S. Nuclear Regulatory Commission. And that we do this work in collaboration with UC Berkeley, INL, Oak Ridge, MIT, the Rez Institute in the Czech Republic, and our collaborators at UW-Madison. What kind of interaction might occur between salt and graphite? And we started by looking at the thermodynamic data that was available on graphite and on salt. And I will use this example to illustrate what an Ellingham diagram is and how one might use it. An Ellingham diagram will plot what we call Gibbs free energy on the y-axis and temperature on the x-axis. And here I've plotted the Gibbs free energy of formation of various fluoride species. So for example, beryllium fluoride and chromium fluoride, graphite fluorides, and fluorinated carbon compounds. And what this Ellingham diagram allows me to do is to predict if carbon will react with a fluoride species to be fluorinated itself. So for example, if beryllium fluoride were to react with carbon to produce CF4, then this line here would have to somehow cross the beryllium fluoride line so that the reaction of this and that would have a negative Gibbs free energy of interaction. From this data, from this Ellingham diagram, we surveyed all of the fluoride compounds that we thought we might have in our mixture of lithium fluoride and beryllium fluoride, and we surveyed a combination of fluorinated carbon compounds that we could find in the database, and we concluded that none of these lines cross these lines, and so there should be absolutely no chemical interaction between carbon and molten fluoride, LiFeBF2. And I'll also highlight that we looked at liquid species and gaseous species, and this was relevant because carbon is a porous material. And so, okay, this is our hypothesis. Nevertheless, we wanted to make sure that we got it right. And so we designed an experiment to test the hypothesis that nothing should happen. It should have been an easy experiment to run. We did a 12-hour exposure at 700 degrees Celsius in a graphite crucible with graphite coupons with salt in the graphite. And so this was done so that we avoid introduction of additional materials in contact with the salt. We wanted to have only graphite and salt, no other metallic components. We characterized the impurities in the salt, we maintained an inert argon atmosphere, and we observed no weight change. So, all right, thermodynamics seems to have predicted what we observed. However, if we look further into the chemical structure of the graphite before and after salt exposure, we found that that was actually not the complete picture. That we found that there were carbon-fluorine bonds that were being formed on the graphite. And so what you see here is an XPS spectrum this is the fluorine spectrum, which does not exist before salt exposure, appears after salt exposure, and then a decomposition of the fluorine peak, it identifies this shoulder, which corresponds to CF bonds. And similarly, if we look at the carbon peak, there's a shoulder that appears that also identifies with CF bonds. And furthermore, what we see is that there's a shift in the sp2 to sp3 ratio. So sp2 relates to planar sheets of graphite. Graphite is made from hexagonal flat sheets that stack on top of each other. And in order for those sheets to be flat, they have what we call an orbital hybridization of sp2 planar. If there are defects introduced in that graphitic sheet structure, it is possible to have an sp3 hybridization, and those corresponds to non-perfect graphite. And so what we see is that after salt exposure, the amount of sp3, so the amount of defects, increases, and in addition to the appearance of the CF bonds. And so how is this possible? Thermodynamics predicted that this shouldn't be possible, and nevertheless it's happening. If we look closer at graphite, here are the graphene sheets. Nuclear graphites are not single crystal graphites. They're not formed out of an infinite sheet of graphite that never ends. They have edges. And those edges are will have sites that are unsatisfied bonds in some shape or another. Maybe there's a lone pair of electrons, maybe there's a triple bond. And these sites are highly reactive. And so when we look up data for graphite in the literature, that data, that Gibbs free energy data on the Ellingham diagram, refers to an average carbon atom far away from any defect in the graphite lattice. But the data for these isolated defect sites, that's not included in the databases. And so it's these sites that were reacting to form fluorinated sites. And then as an example of something that might be reactive enough to fluorinate, this is C6H6, which is benzene, and benzene fluorination is feasible by reaction with beryllium fluoride. Now we postulate that the reaction that's occurring is that carbon is being fluorinated by a metal fluoride, and the metal fluoride is reducing out to a metal. And so to support this hypothesis, we did elemental analysis with depth of the salt-exposed graphite, and what we find is that there are metals on the surface that deposit on the up to 2 microns, so on the exterior surface of the graphite, and then there's fluorination that perseveres into the depth of the graphite. And we also found that the dominant metal at the surface is beryllium. The ratio of beryllium to lithium is 10, and this is supported by thermodynamic data because beryllium is higher on the Ellingham diagram than lithium, and so we expect this to react much more than something that's further down on the Ellingham diagram. The results we get require the postulation of a new reaction, and then they are in line generally with thermodynamic data. This is an example of where thermodynamics works, but it is predicated on picking the right species, picking the right reactants and products. If we haven't imagined the right species, then thermodynamics isn't going to be sufficient. And so then we looked further into the relationship between the crystal structure of graphite and the chemical reactivity. Because the sites, these reactive sites, as I mentioned to you, they can often occur at the edges of graphene sheets, and how many of those edges exist will depend on the crystal size and the crystal structure and the crystal shape. And so we continued to do more work in understanding not just what is the crystal structure of nuclear graphites, but also how does it change upon exposure to the salt. And so we find that it changes and that fluorination creates more defects, which also is in line with the fact that we saw that change in hybridization from planar to not planar. And then lastly, this is Raman analysis, pre-exposure, post-exposure, and we see features in the Raman spectrum that are characteristic of graphite fluorination, and this is a study specifically on graphite fluorination. And so we were quite convinced that this was indeed a phenomenon that was happening. So this was case study number 1. Now, case study number 2, the behavior of hydrogen in molten salt at high temperatures. We did electrochemical studies to probe the diffusivity of hydrogen in molten salt. Now, the diffusivity of hydrogen isotopes in molten salts has previously been done with permeation experiments, where one might have a large metallic vessel or two concentric metallic vessels with an applied pressure of hydrogen or deuterium or tritium on the exterior vessel, and then the hydrogen diffuses through to an inner wall where its pressure is measured. These kinds of installations are extremely involved. They are operated by national laboratories, and it is very difficult to obtain experimental data. There have been only a handful of campaigns of this kind. Instead of relying on the physical process of hydrogen diffusion in the salt, we wanted to use electrochemistry to probe the diffusivity of the solvent. And so electrochemistry allows us to drive specific reactions by applying a potential between two electrodes. So what are electrodes? Electrodes are conductors that we immerse in the salt. So here is a pot of salt in an oven, and these are our electrodes. They're wires, basically. We had a platinum wire and a glassy carbon wire. And so if we apply a potential across these two electrodes, in principle, if we apply just the right potential, we should be able to manipulate this reaction of hydrogen gas going to a hydrogen ion in the salt. So if we have hydrogen gas present in the salt, and we consume it at the surface of our platinum electrode, we will measure a current because we are driving electrons out of the hydrogen. And from that current, we can then deduce how fast is H2 diffusing to the surface of our platinum electrode. This is an electrochemical method that is well established for measuring diffusivities, but the big question we had was, can we manipulate hydrogen electrochemically in the salt? And how are we going to introduce it? Because bubbling a hydrogen gas through the salt is possible, but not trivial. And so what we did instead is we used lithium hydride, which we expect to react with beryllium fluoride and lithium fluoride to produce hydrogen gas in situ. And then hydrogen gas, we would then electrochemically react at the surface of the platinum electrode. And so here in black, you see a potential applied to our platinum electrode, and on the y-axis is current. And we see no signal around the potential where we would expect to see hydrogen occur. And after we add lithium hydride, we sweep again the potential and we see a current. So that means that we are indeed, as thermodynamic data predicted, producing H2 in solution, and we're able to manipulate it. This was great news. We then were able to manipulate H2 to H plus back and forth. And from the rate at which the current was changing with sweep rate or time, we were able to deduce diffusivity data. And so what you see in black are prior experiments. There are 3 experimental data sets that have been measured using permeation experiments, and what you see in green and red are our experimental data. And what is most remarkable is that each of these data points, you will note, have no error bars. Because, again, these permeation experiments are very hard to do. There have been a total of 4 data points collected over the course of decades. Whereas with electrochemical runs, they take about an hour. And so we were able to do every one of these points has a total of about 30 measurements in it. So then we can have statistics and evaluate the error bars. This was quite exciting that we were able to match previous data and then quantify error bars. And there's a lot more development that can be done here to narrow those error bars. So this was an example of a successful use of thermodynamics in making a relatively simple measurement of a thermophysical property that is otherwise very difficult, very challenging to measure. And so case study number 3 relates to acidity and complexation. So here's an example of niobium. Niobium is a fission product, and it would be useful to know its solubility and its volatility. So if we look here at this is a potential, or Gibbs free energy, if you will, similar to the Ellingham diagram. We know that at a given potential, niobium will be 4+, dissolved. Below this potential, it'll be a metal, so it'll precipitate. And then above this potential, it'll be a gas. We had this thermodynamic data. And this seemed like a well-characterized system. However, you'll notice that I covered some information here. So far, all we know is thermodynamic data about oxidation and oxidation reactions, so electron transfer reactions. But we don't know information about complexation. And so here's an example of complexation with oxides. So niobium-5, which would typically be highly volatile, so a gas, something that would bubble out of the salt, can complex with oxygen and form niobium O2-, which is in fact highly soluble. So with less than 1 ppm, parts per million, of oxygen, niobium goes from being highly volatile to being highly soluble. And so this is something that we need to pay very careful attention to. The potential of oxidation, the redox potential, is only one axis on what is actually a two-dimensional space when we characterize the thermodynamics of molten salt systems. And the x-axis is acidity. In water, we would plot with pH on the x-axis and potential on the y-axis. And we would call these diagrams Pourbaix diagrams, and we would use them in predicting corrosion of metals. In molten salts, we do not have Pourbaix diagrams. This is not a Pourbaix diagram. This is a pseudo-Pourbaix diagram. Because in a Pourbaix diagram, we would quantify pH, which would be PO2-. But we don't have methods for measuring PO2- in molten halides. What was measured here was the total sum of O2- uncomplexed. I think the battery is running out. All right, well, that's okay. So I can't move. All right. So the oxide can be complexed or uncomplexed. And the uncomplexed oxide is what we would like to be able to plot on the x-axis as our PO. But because we can't measure, we can't differentiate between complexed and uncomplexed, or at least not at the time of this study in 1977, what they plotted was the total oxide. So we call it a pseudo-Pourbaix diagram that begins to show the importance of acidity, but doesn't quite yet get at a generalizable Pourbaix diagram. And so this is I bring out this example to highlight the importance of acidity in the behavior of melts. And there are many other examples of complexing species that will affect the acidity of the melt, and hopefully we will have both theoretical models and experimental methods for measuring acidity in the salt more readily available to us in the molten salt community. And here is yet another example of how acidity and complex ionic structures will also change the thermophysical properties of the salt. And so here is lithium fluoride, beryllium fluoride, which is known to form complexes, and its density as predicted from an ideal mixture where the constituents mix without restructuring or without forming complex structures, and we would predict a relatively low density, whereas when we actually make these measurements, we find that the density is higher. So when you mix lithium fluoride and beryllium fluoride, they shrink. And why they shrink because they form new structures, and we need to understand what those new structures are. They tie to acidity. So those were 3 case studies of the application of thermodynamics. Again, it's important to postulate what the species are, and again, it's important to postulate what the species are when we talk about complexation and when we talk about reactions. And then once we do get it right, having a thermodynamic understanding of the melts is quite powerful. We can do measurements of thermophysical properties with much simpler methods such as electrochemical methods. I would like to conclude with thanking the students in my group that do a lot of the experimental and modeling work on molten fluorides. And we do a lot of work with lithium fluoride, beryllium fluoride. Beryllium fluoride is highly toxic. And so these are the safety standards that we adhere to. And on our website, you will find our procedures for beryllium safety for the sake of transparency and also for the sake of sharing the knowledge. And please comment if you think there's a better way to do it. And there's also a teaching tab where I post my lecture notes from the molten salt reactor course that I teach. And then I will mention that so far we've had 28 students that have trained in our labs, and we're always looking for new students, and we always also have students that are graduating and looking for jobs. And I'd like to thank my group and thank you for your attention, and I'd love to take some comments and questions.
Thank you. You have a question here?
So your students are finding jobs easily, one?
Well, they are, yes.
Second, where do you get lithium-7?
So lithium-7, we haven't had to use it yet. It is useful in neutron diffraction studies so that we can differentiate between lithium and beryllium when we look at the structure of FLIBE melts. And we have that from the MSRE program from Oak Ridge. Yes, we work quite closely with Oak Ridge National Laboratory.
On what you said about measuring oxo-acidity in the melts.
Yes.
I believe there are ways of doing it in fluoride salts. In other melts, such as lead-bismuth eutectic and oxygen-containing melts, you usually use an yttria-stabilized zirconia as an electrode that would then detect the oxide ions. I'm not sure if those work so well in fluorides because they can deteriorate, but I think there's maybe things with bismuth and bismuth oxide metals. But I can't remember off the top of my head what the solutions are.
They've been shown to be sufficiently stable in chlorides, not so much in fluorides. Typically, oxides have high solubility in fluorides, so if we could have a thick membrane and it would still work for a short amount of time, but the concern is that we're contaminating the melt with more oxide. So it's definitely possible, and we're working towards that, but having a magic membrane that's sensitive to O2 minus specifically, or F minus specifically, or I minus specifically is definitely, we're always on the lookout for that. Yes?
You kept showing those really nice pictures of the two bubbles and of the droplets on the
yes.
graphite layer. What can you tell me using these pictures about the wettability of graphite and the consequences for design or nucleation?
Quite a bit. Thank you for the question. So this is FLIBE and this is FLINAC and this is FLIBE, and in this case they're non-wetting on nuclear graphite. We know that the wetting behavior is highly sensitive to the chemical environment. Moisture and oxygen leads to higher wettability. Pre-treatment of the graphite before exposure to the salt droplets will affect the chemistry of the salt, which in turn affects wettability. And we have an active study on contact angle and wetting and surface tension, and I can tell you more about that and point you to some publications if you're interested. Your other question was about nucleation, and we also use this same setup with the video version of it to look at solidification studies. We're interested in modeling and characterizing freezing, especially with fluids that supercool, and FLIBE is one fluid that can supercool down to 50 degrees or maybe even more. So in videos of FLINAC freezing, you will see that it nucleates homogeneously. There are crystals that form in the bulk of the FLINAC that then drop down.
Because it's interesting how the nucleation works. I was thinking about nucleation of non-condensables.
Of non-condensable gases. We have not done that work yet. but it's definitely something that would be interesting to work on.
Yeah, you've shown that some fluorine or metals are deposited on graphite. Is that a problem in any way for a graphite molten salt reactor?
It has importance for tritium uptake and also for surface properties such as lubrication and friction, and it can also have impact on the wetting behavior. And it has very important implications for corrosion, for metal alloy corrosion, because graphite, it begins to explain why graphite can accelerate corrosion of metal alloys. So yes, it is highly important to understand this.
Okay, with that, let's thank Raluca again. And now it's lunchtime.